They built atmospheric engines in the 1800s that drew energy directly from the air. There is an entire category of engines developed and operated commercially in the 19th century that most people have never heard of, but which powered mines, factories, and pumping systems for decades in multiple countries. They weren't steam-powered in the way we traditionally think of them. They didn't burn fuel to create direct expansion of hot gases. Instead, they used natural atmospheric pressure. Differences to generate measurable mechanical force and perform real useful work. Called atmospheric engines or atmospheric fire machines, these devices represented an ingenious application of fundamental physical principles that anyone can understand. Air at different temperatures occupies different volumes, and changes in volume can be converted into mechanical motion through pistons and cylinders. The reason these engines seem mysterious today is not because they were suppressed or hidden, but because they were eventually replaced by high-pressure steam engines that were more compact, more efficient, and more versatile. But for roughly a century, from the mid-1600s to the mid-1700s, and in some applications until the early 1800s, atmospheric engines were cutting-edge, utterly practical technology for pumping water from deep mines and other specific industrial applications. Understanding how they worked offers a fascinating lesson in human ingenuity working with the material. Limitations and scientific knowledge of the time. It also demonstrates an important principle. Technologies don't need to be the most theoretically efficient to be commercially viable and historically significant. They only need to solve a real problem better than the alternatives available at the time. This roadmap explores 10 progressive aspects of atmospheric engines, from basic physical principles to documented practical implementations, explaining exactly how engineers in the 1600s and 1700s managed to extract mechanical work from atmospheric pressure differences using materials and knowledge available at the time. We begin with the most fundamental physical principle that makes these engines possible. If you're intrigued by the idea that 17th and 18th century engineers developed functional engines that operated through atmospheric pressure differences and were used commercially for decades, leave a like supporting the exploration of real historical technologies based on verifiable physics. Subscribe for documented historical engineering analysis through preserved records and patents. Turn on notifications for investigations into how technologies actually worked technically. If you value an approach that explains real physics and engineering without resorting to conspiracy theories about suppressed technology, click the Hypar button supporting educational content based on verifiable science. The first fundamental physical principle begins now. Heated. Air expands and cooled air contracts, creating measurable pressure differences. Physical principle number 1, thermal expansion of gases. All gases, including ordinary atmospheric air, expand when heated and contract when cooled. This is not an abstract observation. It is a measurable, quantifiable phenomenon that anyone can verify with simple experiments. When you heat a fixed volume of air in a closed container, gas molecules move faster and occupy more space, increasing pressure if volume is kept constant. When you cool the same volume of air, molecules slow down and occupy less space, decreasing pressure. This principle is formalized in the ideal gas law, which relates pressure, volume, and temperature. For the purposes of 17th century atmospheric engines, the relevant relationship is simple. If you have a cylinder with a movable piston and you heat air inside the cylinder, the expanding air pushes the piston upward against external atmospheric pressure. If you then cool this air rapidly, it contracts, creating a partial vacuum inside the cylinder, and external atmospheric pressure pushes the piston downward with considerable force. The ingenuity of atmospheric engines lay in using this heating and cooling cycle repeatedly to create usable reciprocating motion. But there was a crucial challenge: how to heat and cool air inside the cylinder quickly enough for a practical cycle. Simply heating air directly with fire and then waiting for it to cool naturally would be extremely slow and inefficient. The ingenious solution developed by Thomas Newcomen and others was not to heat the air directly, but to use water vapor as an intermediary. Steam is created outside the cylinder in a separate boiler by heating water with coal or wood fire. This hot steam is then admitted into the cylinder, pushing air out. Hot steam occupies much more volume than the liquid water that generated it. When steam fills the cylinder, it pushes the piston upwards. Then, and this is the crucial part, a jet of cold water is injected directly into the steam-filled cylinder. Cold water instantly condenses the steam back into a liquid state that occupies a minuscule volume compared to the steam. This sudden condensation creates a partial vacuum inside the cylinder. External atmospheric pressure, acting on the top of the piston, which is exposed to ambient air, pushes the piston downwards with tremendous force. This is the part of the cycle that actually performs useful work. The descending piston can be connected to a rod that drives a water pump, lifts weight, or performs other mechanical work. The beauty of this system is that the downward force does not come from burning fuel directly under the piston. It comes from natural atmospheric pressure pushing against a vacuum created by the condensation of steam. That is why they are called atmospheric engines. The atmosphere provides the main driving force. Steam is merely a means of creating and rapidly destroying a vacuum. Partial vacuum created by condensation allows atmospheric pressure to perform real work. Physical principle number 2. Atmospheric pressure as a source of force. Atmospheric pressure at sea level is approximately 101,325 pascals. On each square centimeter of surface exposed to air, the atmosphere pushes with a force of approximately 1 kilogram. When you create a vacuum on one side of a surface, the imbalance becomes dramatic. A cylinder with a cross-sectional area of 1 square meter and a near-complete vacuum inside receives atmospheric pressure, pushing a piston with a force of approximately 10 tons. 18th century atmospheric engines typically had cylinders with diameters of 50 to 70 centimeters. With a diameter of 60 centimeters, a reasonable partial vacuum would create a downward force of about 2 to 3 tons, sufficient to power deep pumps. The challenge was to create this vacuum quickly and reliably. Vapor condensation was a brilliant solution. When water vapor condenses back into liquid, the volume decreases by a factor of approximately 1,600 times. Injecting cold water into a cylinder full of steam condenses the steam almost instantly, creating a partial vacuum. The pressure differential between the exterior of the piston exposed to atmospheric air and the interior exposed to vacuum creates an enormous force pushing the piston downwards. This is the power stroke of the atmospheric engine. After the piston descends completely, fresh steam is admitted again, pushing condensed water out and filling the cylinder. The piston returns to its upper position by weight or spring. Then the cycle repeats. Thomas Newcomen developed the first commercially viable atmospheric engine in 1712. Historical development number 1, Newcomen's atmospheric engine. Thomas Newcomen was an English blacksmith and toolmaker from Dartmouth who worked for over 10 years developing a practical atmospheric engine. His first documented an operational engine was installed in 1712 in a coal mine near Dudley Castle in Staffordshire, England. This engine was specifically built to pump water from deep coal mines, a critical problem that limited mining. The deeper the mine, the more groundwater seeped in, and existing pumping methods using horses or windmills were inadequate for great depths. Newcomen's engine consisted of key components: a large boiler that generated steam by continuously burning coal, a vertical metal cylinder, usually made of cast iron with a fitted piston inside, a piston rod connected to a large oscillating beam of wood or metal, and a valve system controlling steam intake and cooling water injection. The operational sequence was: steam valve opens, allowing steam from the boiler to fill the cylinder and push the piston upwards. Steam valve closes. Water injection valve opens, allowing a jet of cold water to enter the cylinder. Water instantly condenses into steam, creating a partial vacuum. Atmospheric pressure pushes the piston down rapidly with tremendous force. The drain valve opens, allowing condensed water to drain from the cylinder. The steam valve reopens, admitting fresh steam, and the cycle begins again. In early Newcomen engines, valves were manually operated by an assistant who observed the piston's position and opened and closed the valves at the correct moment. A famous but possibly apocryphal story tells of a boy named Humphrey Potter who operated the valves, who became bored and tied the valve ropes to the oscillating beam itself so that the beam's movement automatically opened and closed the valves. True or not, automatic valve systems mechanically controlled by the engine's own movement quickly became standard. The 1712 Newcomen engine had a cylinder with a diameter of approximately 50 centimeters and performed about 12 cycles per minute. Each stroke lifted approximately 45 liters of water from a depth of approximately 50 meters. This resulted in a pumping capacity of over 30,000 liters per hour, far superior to any previous method. The engine was an immediate success, and Newcomen engines were installed in mines throughout England, then Scotland, and eventually continental Europe in the following decades. By around 1775, estimates suggest that over 100 Newcomen engines were operating in the coal mines of Cornwall alone. These engines operated reliably for decades. Some specific engines ran continuously, with regular maintenance for over 50 years. The reliability came from a simple design with few moving parts and a relatively low operating speed that minimized wear. The atmospheric engine used a large oscillating beam to transfer motion from the piston. Mechanical component number 1, rocker beam or rocker arm. The most visually distinctive feature of Newcomen atmospheric engines was the enormous rocker beam, usually of reinforced wood or iron, which pivoted at a high central point. This beam could be 10 to 15 meters long in large engines. The piston rod was connected to one end of the beam. The water pump rod was connected to the other end. When the piston in the cylinder was pushed down by atmospheric pressure, the end of the beam connected to the piston descended and the opposite end rose, pulling the pump rod upwards. This lifted water through vertical pipes from deep within the mine. When the piston returned to its upper position, due to weight or counterweight, the beam rocked back and the pump rod descended, allowing the bottom valve in the pump to open and more water to enter. The next cycle lifted this water higher. The rocker beam served multiple essential functions. First, it transferred vertical motion from the piston to vertical motion of the pump, located possibly several meters away. Second, through careful design of beam arm lengths, it was possible to multiply or modify force and distance of movement. Third, the mass of the beam itself, plus any added counterweight provided return force that pushed the piston back up after power stroke. Fourth, the beam's oscillatory movement was externally visible, allowing operators to monitor whether the engine was functioning correctly without needing to observe the inside of the cylinder. Atmospheric engine beams were often impressive engineering feats in themselves. They needed to be strong enough to withstand forces of several tons, but also needed to be carefully balanced to oscillate smoothly without excessive vibration. The central pivot point was supported by an extremely robust masonry or metal structure called the engine house. The structure needed to support not only the weight of the beam, but also the dynamic forces of continuous operation. In some large engines, the beam weighed several tons. Wood was often preferred to metal for beams because it had a better strength-to-weight ratio and was easier to adjust and repair. Hardwoods like oak were used. Metal beams became more common in the late 18th century when iron casting improved. The oscillating beam design also allowed for the installation of multiple motors working in parallel. 2 or more beams could be connected to increase pumping capacity. This modularity was a significant advantage for growing mining operations. Beam movement could also drive not only pumps, but other mechanisms. Some installations used beam movement to power bellows that supplied air for smelting operations, or to lift materials through cable and pulley systems. The coal-fired boiler generated steam continuously to power the engine's repeated cycles. Mechanical component number 2, boiler system. The atmospheric engine boiler was a large metal vessel where water was heated to boiling point to continuously produce steam. It was not a high-pressure boiler. Steam was generated only slightly above atmospheric pressure, typically 1.1 to 1.2 atmospheres. This low pressure was intentional and safe, preventing the risk of explosions. The boiler was heated by a furnace burning coal or wood below. Combustion air entered through a grate, allowing the coal to burn completely. Hot gases passed around tubes in the boiler, transferring heat to the water before escaping through the chimney. Water needed to be kept at a consistent level. Operators monitored it through glass tubes and added water periodically. Clean water prevented the accumulation of minerals that would reduce efficiency. Generated steam flowed through an insulated tube to the cylinder intake valve. Safety included pressure relief valves that automatically released steam if the pressure exceeded a safe limit. These were simple mechanical valves held closed by a known weight. Boilers required constant attention. The operator needed to keep the fire fed, monitor the water level, observe steam pressure, and respond to irregularities. This was a position of significant responsibility because negligence could lead to engine shutdown or boiler failure. Valves controlled precise timings for steam intake and water injection. Mechanical component number 3, valve system. Proper functioning of the atmospheric engine depended absolutely on valves opening and closing in precise sequence. There were typically 4 main valves: steam intake valve, controlling steam entry from the boiler into the cylinder; water injection valve, controlling cold cooling water entry into the cylinder; drain or exhaust valve, allowing condensate to exit the cylinder; and balance or breather valve, allowing air to enter above the piston. In early Newcomen engines, valves were operated manually by an assistant observing piston movement. When the piston reached top, the assistant opened the water injection valve. When the piston reached bottom, the assistant closed the water valve and opened the steam valve for the next cycle. The manual system was laborious and subject to human error. A critical development was the automation of valves through a mechanism called AEE, valve lever or valve shaft, connected directly to the sway bar. When the bar swung, movement was transferred through a system of rods and levers to open and close valves at the exact correct moment. Specific designs varied, but the principle was to use the beam position, which reflected the piston position, to automatically actuate valves. This automation allowed the engine to operate continuously without constant human intervention. Valves needed to be robust and create a hermetic seal when closed. Steam leakage through the intake valve wasted fuel. Air leakage through the drain valve reduced vacuum and efficiency. Valves were typically gate or globe type, made of metal with carefully machined sealing surfaces. Some used leather or hemp packing to improve sealing. Valve wear was a common maintenance problem. Repeated operation thousands of times a day gradually degraded sealing surfaces. Regular maintenance included inspecting and remachining or replacing valves as needed. Some advanced engines included an additional safety valve that would automatically shut off the steam supply if cylinder pressure became abnormally high. This prevented damage to the equipment in case of malfunction of other valves. Precise valve timing was adjusted to optimize efficiency. Opening the water injection valve too early wasted water and reduced the vacuum eventually created. Opening too late allowed the steam to cool partially, losing energy. Experienced engineers fine-tuned the timing through small changes in the valve mechanism, observing fuel consumption and work output. A metal piston, precisely fitted inside a cylinder, transferred force to the beam. Mechanical component number 4, piston and cylinder. The heart of the atmospheric engine was a vertical metal cylinder with a precisely fitted piston inside. The cylinder was typically made of cast iron through a casting process and then machined internally to create a smooth, uniform surface. The internal diameter needed to be consistent along its length for the piston to move freely without seizing. Newcomen engine cylinders ranged from 40 centimeters to over 2 meters in diameter depending on the application. Depth was typically 1 to 2 times the diameter. The piston was a solid disc, also made of cast iron, fitted to slide inside the cylinder, with minimal but sufficient clearance to allow free movement. Too much clearance would allow vapor and air to escape around the piston, reducing efficiency. Too little clearance would cause friction and wear. Achieving proper fit required careful machining. Sealing between the piston and cylinder wall was a significant challenge. A metal piston in a metal cylinder never seals perfectly. Some leakage always occurs. The solution was to cover the top of the piston with a layer of water, creating a liquid seal. Water filled irregularities and prevented gases from escaping around the piston rim. Operators periodically added water to the top of the piston to maintain a seal. The piston rod extended vertically upwards through the top of the cylinder and connected to the rocker beam. The point where the rod passed through the top of the cylinder needed to allow free movement, but also minimize steam leakage. A string packing soaked in grease or other sealant material was pressed around the rod, where it passed through the cylinder head. The piston and cylinder experienced significant mechanical and thermal stress during operation. The piston was alternately heated by hot steam and cooled by injected cold water. Thermal expansion and contraction could cause wear and eventually distortion. Regular inspection and maintenance were necessary. Every few months, the engine would be stopped, the cylinder opened, and the piston inspected for wear, cracks, or deformation. The inner surface of the cylinder was also inspected for corrosion or uneven wear. Repairs might involve remachining surfaces or replacing components. The service life of a well-maintained piston and cylinder could be decades. Some Newcomen engines operated for 50 years or more with periodic replacements of worn components, but using the same basic cylinder structure. Thermal efficiency was low, but the engine solved the real problem better than alternatives. Practical limitation number 1, energy efficiency. Newcomen atmospheric engines were inefficient by modern standards. Thermal efficiency was only 1 to 2%, 98 to 99% of the energy from the burned coal was lost as heat. Why? First, steam contained relatively little energy compared to high-pressure steam. Second, cold water injected to condense steam also cooled the metal walls of the cylinder. In the next cycle, when fresh steam entered, some of its energy was wasted reheating the cylinder. This alternating heating and cooling of the cylinder was the main loss. Third, condensation was never complete. There was always residual steam and air, reducing vacuum. Despite low efficiency, Newcomen engines were economically viable because coal was abundant and cheap in mining areas. Mines had unlimited access to lower quality coal unsuitable for sale. Even consuming enormous quantities, the cost of fuel was acceptable compared to the value of keeping the mine operational. John Smeaton made incremental improvements to the design in the 1770s that increased efficiency by about 50% through better sealing, more precise cylinders, and improved insulation. But a revolutionary advance came from James Watt, who in the 1760s realized that heat loss could be eliminated with a separate condenser kept permanently cold, leaving the main cylinder continuously hot. This innovation increased efficiency by a factor of 3 to 4. Watt engines gradually replaced Newcomen engines in applications where efficiency mattered. But in coal mines, where fuel was essentially free, some Newcomen engines continued to operate until the early 19th century because they were simpler and cheaper to build and maintain. Technically, better technology does not always immediately replace inferior technology if older technology still adequately solves the problem at an acceptable cost. Hundreds of engines were built and operated commercially for decades, as documented. Historical implementation number 2, widespread use and longevity. Atmospheric engines were not laboratory experiments or curiosities. They were large-scale industrial installations operating commercially for decades. Historical records document over 1,400 Newcomen engines built between 1712 and 1800 in England, Scotland, Wales, France, Germany, Belgium, Sweden, and other European countries. Most were installed in coal, tin, copper, and lead mines for pumping water, but some were used for urban water supply, swamp drainage, and even feeding bellows for smelting furnaces. The operational longevity of individual engines was impressive. The Newcomen engine installed at Griff Colliery near Coventry in 1714 operated continuously until 1820, over 100 years. The engine in Ashton-under-Lyne installed in 1760 ran until 1834. These were not museum preserves. They were working machines operating daily, performing commercially essential work. Regular maintenance was obviously necessary, but the basic structure and operating principle remained the same for decades. Detailed documentation exists describing specific engines. John Smeaton published technical accounts of his studies of Newcomen engines, including measurements of cylinder dimensions, coal consumption, volume of water pumped, and efficiency calculations. These documents allow modern engineers to reconstruct exactly how the engines worked. Some Newcomen engine installations still exist as preserved historical monuments. The engine house in Elsecar near Barnsley in England preserves a Newcomen engine from 1795 that operated until 1923. The building and oscillating beam remain on site. The atmospheric engine in Dartmouth, where Newcomen lived, has a working replica demonstrating operating principles. These historical sites confirm that engines were real, substantial, and technically sophisticated for their time. The economic impact of atmospheric engines was significant. They allowed deep mining that would not have been possible with previous methods. This increased the supply of coal, which fueled the Industrial Revolution. It also spurred developments in metallurgy and precision machining necessary for manufacturing cylinders and pistons. Workshops that manufactured Newcomen engines became centers of expertise in mechanical engineering, training generations of engineers and craftsmen. James Watt improved fundamental design with separate capacitor, increasing efficiency. Historical development. Number 2, James Watt's improvements. James Watt was an instrument maker working at the University of Glasgow when, in 1764, he was asked to repair a model of a Newcomen engine used for demonstrations. While studying the model, Watt realized a fundamental inefficiency. A cylinder alternately heated by steam and cooled by injected water wasted a huge amount of energy. Watt devised a solution: a separate condenser. Instead of condensing steam inside the working cylinder, steam would be directed through a valve to a separate container kept permanently cold. Vacuum created by condensation in this separate container would pull the piston down through a tube connected to the main cylinder. The main cylinder would remain continuously hot because it would not be cooled by condensation water. This seemingly simple change had a dramatic impact. Efficiency immediately increased by a factor of 3 to 4. Less coal was needed to produce the same amount of work. Watt patented the separate condenser in 1769 and spent subsequent decades developing further improvements. He added a steam jacket around the cylinder to keep it hot. He developed an elegant parallel motion mechanism that converted vertical motion of the piston rod into more uniform motion of the beam. He created a centrifugal governor that automatically controlled steam input based on engine speed, maintaining stable operation. He introduced a double-acting engine where steam alternately pushed the piston up and down instead of relying solely on atmospheric pressure for power stroke. Watt's partnership with businessman Matthew Boulton led to the commercial production of Watt engines from the 1770s onward. These engines gradually replaced Newcomen engines in applications where fuel efficiency justified higher manufacturing costs and greater complexity. Interestingly, Watt kept steam pressure relatively low in his engines for safety reasons. He feared high-pressure boilers. It was only with Richard Trevithick and others in the early 19th century that truly compact and powerful high-pressure steam engines were developed. But Watt's contributions to efficiency and control laid the foundation for the steam age. Importantly, Watt's improvements did not invalidate Newcomen's achievements. Newcomen created the first commercially viable practical atmospheric engine. Watt improved its efficiency dramatically. Both were essential steps in the development of steam engine technology, and both were based on fundamental physical principles of thermal expansion of gases and atmospheric pressure that anyone can understand and verify. If these 10 aspects of atmospheric engines from the 1700s, from the physical principles of thermal expansion of gases and the force of atmospheric pressure to documented practical implementations in hundreds of installations operating commercially for decades, demonstrate that this technology was real, based on verifiable physics, and historically significant, not suppressed or hidden, but eventually superseded by more efficient designs. Leave a like supporting the exploration of historical engineering through documented evidence. Subscribe for analyses of real technologies that actually existed and worked based on sound scientific principles. Click on the video appearing on the screen to delve deeper into the development of steam engines and the transition from atmospheric to high-pressure design. Thank you very much for taking the time to understand how 17th and 18th century engineers managed to extract mechanical work from atmospheric pressure differences using the knowledge and materials available in their time. See you in the next exploration of real verifiable historical technology.